the seminar today. Samuel actually was born in Houston. His family still lives there, so he's been coming of some sort. So Samuel actually decided not to stay in Texas to go to school. He was an undergraduate at Caltech. Oh, no, sorry, graduate student at Caltech. I forgot where he was undergrad. And he worked there with his advisor, Mark Hamikowski, when Mark was there. Lots of interesting subjects like the interface of astroparticle physics and cosmology with Mark. Then he got a postdoc and has been there ever since at the Princeton Center for Theoretical Science, which we just learned is very synergistic. So I'm sure he'll give a very synergistic talk about the GEV, the mystery of the GEV access.
Thank you. First of all, yeah, thanks for the invitation to speak. I'm glad to have the opportunity to tell you a little bit about the mystery of the GEV access. I can't promise that I'll do too much unraveling of this mystery, but we'll see how it goes. Okay. Right, so here's an overview of my talk. Many of you may have heard of this GEV excess of gamma rays as observed by Fermi in the Galactic Center. And the reason why a lot of people have been excited about this is this could be tantalizing evidence for dark matter annihilation coming from the Galactic Center. However, the excess could also be arising from more mundane astrophysics. And in this talk, I'll try to elucidate some ways we can distinguish between these possibilities. And in particular, I'll be talking about tests of these astrophysical scenarios. One test involves the photon statistics of the gamma ray counts. And the second set of tests involves wavelength decomposition of the gamma ray data. Okay, well, so let's start off by looking at the Fermi gamma ray sky. So here's a counts map from Fermi. I think this is about 5.5 years of data. And you can see that there are some very interesting features in the gamma ray sky. Most prominent is the dominant galactic diffuse emission. You can see this plane here. If you've got really good eyes, you can see the Fermi bubbles. Maybe you can't see them. I guess that's why they give those high energy astrophysics prizes. You got good eyes. Fermi bubbles are there. You can also see at high latitudes, maybe it's easier to see many, many point sources. So these are typically AGN, millisecond pulsars, etc. Okay. Now, so there's very many components in the gamma ray sky. We can take our best fit models of these components, and here I'm showing the best fit model for the galactic diffuse emission and also the bubbles. I think they're a little more prominent there.
You said unprominent?
Sorry, where? So here, this is just the diffuse emission. There's a mask galactic center there, but that's right. So Andromeda viewpoint sources, and we can put that here.
Actually, would it be down there? Yeah, that's what I was talking about.
We were just discussing it.
Oh, I'm sorry, that's the opposite. Never mind.
We were just discussing my credentials as an astronomer, so I won't say whether or not I know where Andromeda is. Sorry. So okay. So here's the best fit diffuse and bubbles, and if we take this model, subtract it from the data, and additionally model the point sources that we see and identify, we are left with residuals. And in particular here I'm showing a plot from a paper Dailan et al. So here is the flux map in 3 different energy bins of a small region around galactic center. And here is the residual left over when you subtracted those best fit models. And you can see there's a clear excess that's right smack dab at galactic center. In fact, if you zoom out a bit, this excess actually extends to what we call the intergalaxy region. So here we're zooming out to about 40 by 40 degree region. Again, residuals in different energy bins. And you can see this excess extends out to around 10 degrees. Okay. Now you can try to extract the spectrum of this excess component, and many groups have done this. And they consistently see that it has this bump-like feature, with the peak occurring around 2 GeV, and tails extending out to about anywhere from 10 to 100 GeV, depending on how the fit is done.
How do you define the error?
Sorry?
How do you define
The error. So here the error, there's statistical here, but there's also systematic errors that are not accounted for, right? So as I said, many groups have now independently confirmed the existence of the excess, going all the way back to 2009 by some people's accounting. And it seems like all of these studies have sort of converged. So as I showed you, they all agree that this spectrum, this excess component, is relatively hard, has a peak that's pretty robustly at 2 GeV.
Do they all use the same background model, like the diffuse background?
So there's variation. I mean, so there's been improvements in the diffuse model as these studies have been released, so there's definitely some variations in the exact details of the spectrum that they extract. I'll show you some of that later. But it's the peak is quite robust, and it seems to be harder than, or relatively hard compared to other components in the sky. So that's one characteristic. The second is that this thing seems to be roughly spherically symmetric, and it has an intensity profile that falls off as a power law with distance away from galactic center, and extends again out to about 10 degrees. Okay, so that's a quick overview of the characteristics of the excess. Now I'm going to briefly tell you why some people think this excess might be arising from dark matter annihilation. And since I'm guessing all of you know what dark matter is, know what dark matter annihilation is, I'm going to spare you pie charts and things like this, and we're going to jump right into it. Okay, so the properties of the excess are consistent with some of the conventionally held predictions for indirect detection of WIMP annihilation. In particular, that spectrum that I showed you could roughly be consistent with a WIMP annihilating to BB bar if it has a mass of around 30 GeV, or alternatively a 10 GeV WIMP annihilating to tau leptons. And secondly, that intensity profile is pretty much follows what's been classically predicted for annihilation in an NFW dark matter halo. So again, we observe that this thing falls off with angle in this way. Here I'm writing down this standard expression for the intensity profile as a function of angle for dark matter annihilation. This thing goes as the density of the dark matter squared, because you need this to annihilate. And numerical simulations suggest that this density profile should follow an NFW profile, which is roughly given by this, form. And it turns out that depending on what the index is here, you can easily get this power law fall off, right? So maybe this isn't so convincing. You see some signal that falls off as a power law, you say, yeah, well, that's consistent with NFW, but that's the general picture.
Sorry, so a lot of recent work has shown that the NFW profile does not follow all the way into the
Right.
core. So would that change the power law index?
Right. So you can just throw in a different profile here. I think. So first of all, the classic NFW profile is for a gamma of 1, right? And so, right. So even for this signal, the gamma is not equal to 1. But people make arguments. They say, well, this thing could be adiabatically contracted. It could have different index close in the interior, and so it's roughly consistent with what we expect. But in the end, it's the power law. Right? Okay. Right. And the third thing is that the annihilation cross section that you need in order to get the normalization of the observed excess is right around the cross-section you need for thermal abundance, thermal production of dark matter. So here I'm showing the standard annihilation cross-section versus mass plot. Here are those two cases for annihilation of BB bar, the taus, and you can see this falls right around thermal, around 10 to the minus 26. Okay, so that seems to be evidence for dark matter annihilation coming from the galactic center. But of course, we can look for dark matter annihilation from other regions in the sky that we expect to have high concentrations of dark matter, in particular dwarfs, which Louis knows much about. Here I'm showing some constraints from both the LMC, which is this red line, and from dwarf galaxies, which is this blue line. There was just a couple days ago a better constraint release.
Actually, it's no longer coming primary.
Right. Right. So this is from the LMC paper. Sorry. Right, so it seems the case that there is some tension between the positive observation at the galactic center and the null result from the dwarfs. Okay. However, the plot thickens. Just a couple days ago, we discovered a whole slew of new dwarfs, 8 or 9, depending on who you ask. And it seems that one of these dwarfs, again, depending on who you ask, might also display an excess that's roughly consistent with the one that we see at galactic center. So here, around 1 to 10 GeV, you see a little bump. It's quite mysterious. Okay, so that's the case for, against, if you take the dwarf constraint into account, dark matter annihilation. Now I'll run through a few of the astrophysical scenarios that could be explanations for the excess. Okay, so maybe the most mundane explanation is that we see an excess above a background. Maybe we just got the background wrong, right? And so what is the background in this case? Well, as I said, the most dominant component is coming from galactic diffuse emission, which itself has different subcomponents. So you can see there are gamma rays coming from pion decay and Bremsstrahlung processes that are associated with the interstellar medium, and also from inverse Compton scattering, which is coming from energetic cosmic ray electrons scattering upscattering starlight to produce gamma rays. So these background models are generally modeled using cosmic ray propagation codes, such as GalProp, and there's quite a lot of systematic uncertainty in these models. However, a nice study by Calori et al. Found that even when you take these systematic uncertainties into account, if you try to extract the signal, assuming these different wildly different background models, you still pretty robustly get a nice excess from the galactic center. So it seems to be the case that probably systematic uncertainties in the diffuse background can't get rid of the signal. Okay, so if it's not background, then maybe it's just not dark matter. Maybe it's something else. Another candidate that has been proposed is that these gamma rays are coming from a population of pulsars at the galactic center. And one strong piece of evidence for this is that if you just take a look at the spectrum of the observed pulsars, or the observed globular clusters, which are assumed to contain many millisecond pulsars, you can see that these spectra also have a peak, pretty much exactly at 2 GeV. Now the spectra of these pulsars is a little bit softer, but you can wave your hands and say, well, this is at low energies, there's lots of systematic uncertainty there, I don't know what's going on. Okay, so that's one piece of evidence for pulsars. Another is that it's kind of indirect. So if you looked at the bulge of M31, and you look for the distribution of low mass X-ray binaries, these are thought to be progenitors of millisecond pulsars, and you observe their spatial distribution. It turns out that if LMXBs in our own galaxy, and therefore MSPs in our own galaxy, trace the same distribution as that observed in M31, then the intensity from such a distribution would mimic exactly that of this NFW dark matter annihilation signal. That is to say, you look at the LMXB distribution in M31, it has this power law fall off, and if you run through the numbers, the power law basically exactly corresponds to the power law observed for the intensity profile of the excess. Okay, so that's very mysterious. However, one piece of evidence against pulsars is that, well, Fermi observes around 60 millisecond pulsars. It's positively detected around 60. And many of these are very bright and nearby. But you could say, well, let's take a look at them, and let's write down their luminosity function. And now let's assume that pulsars at the galactic center have the exact same luminosity function. It turns out that you would need many, many more pulsars at the galactic center than are observed in order to generate the excess. That's assuming that we've got this luminosity function correct from these 60 observed pulsars, and that we know well the spatial distribution of the pulsars at the galactic center. So I think the punchline to take away from the millisecond pulsar story is, well, the spectrum looks suspiciously similar, but if these are indeed millisecond pulsars, or indeed a completely new class of gamma ray point sources at galactic center, it would have to be completely unknown to existing gamma ray data. Okay, so that's pulsars and point sources. Another class of scenarios is that perhaps there was some energetic event in the galaxy's past that occurred at the galactic center. For example, an injection of cosmic rays that we're now seeing the gamma ray afterglows of, and this is producing the excess. And you can further divide this scenario into two possibilities. Either the cosmic rays that are injected are hadronic or leptonic. So for example, if you inject a bunch of cosmic ray protons, say thousands of years ago, these things will diffuse, interact with the interstellar medium, and give you this nice gamma ray afterglow. Now, one piece of evidence against this scenario is that if you inject protons, these things primarily interact with the gas. And so this extra signal, this excess, is going to trace primarily the gas. And it doesn't seem like the observed excess traces the gas. It seems to prefer a more spherically symmetric profile. So that's one piece of evidence against that. In the second scenario, you don't inject protons or hadronic cosmic rays, you inject leptonic cosmic rays. And these things will primarily contribute to the inverse Compton component. And so you can see that here the signal, the excess that's introduced is more large scale and smooth. And so this scenario has I think there are less objections to this scenario. Right, okay. So it seems like there are a bunch of different possibilities. I don't know, does anybody want to take a vote which way they believe? Maybe not. Oh, we are being videotaped after all. But I think a good way to approach this is, it would be great if the signal is dark matter. That'd be awesome. But I think in order to be confident that this is a robust observation of dark matter annihilation, you really need to look at all the alternative scenarios and try to rule them out as best as you can with the data. And it's possible that the data might not be good enough to rule these out. It's possible that the predictions between dark matter annihilation and these alternative scenarios are so close that there's no practical distinction. Or it might be the case that you apply some of these tests to the data and you find that one of these alternative scenarios is preferred. So I think any of those possibilities is interesting, and it's definitely worth taking a closer look at. Okay, right, so now I'm going to start talking about my own work. Now both of these projects are very recent, and these are, again, focusing on tests that could possibly probe these alternative astrophysical scenarios. Now, the first one I'll talk about is how we might be able to use photon statistics to constrain the point source scenario, the millisecond pulsar scenario. And one with some collaborators at Princeton and now at MIT. So the first study we released, the paper, in December, and here we use simulated data to see whether it's even viable to use such a statistical test. And once we completed that paper, found out it wasn't such a ridiculous idea. Now we're applying it to the real data, and that is ongoing. Okay, and the second project I'll tell you a little about is wavelet decomposition techniques and using these on the Fermi data. And as we'll see, these can tell us a little bit about the angular scale properties of the excess, and they constrain, for example, the hadronic cosmic ray injection scenario. And this is with Sam McDermott, Elias Cholos, and Patty Fox. Okay, so let's start off with the photon statistics and constraining point sources. So here I'm showing two simulated excesses. One of these comes from a smooth NFW profile and dark matter annihilating within it, and the other comes from an NFW distributed population of millisecond pulsars or point sources more generally. So I think it's pretty obvious which one is which. Right? These are the point sources. This thing is much more smooth. Here you can see much more discrete structure. Right? So that's the case if there was no background or foreground. But here's what the picture looks like if you throw in the galactic diffuse emission. And so I think just by looking at these, a priori it would be hard to say which one contains dark matter and which one contains point sources. And so you have to resort to a statistical detection of these point sources. Now you might say, here I can see a few bright spots, right? And so these are indeed the detected or resolved point sources that Fermi sees and puts in its catalog. But the point we're trying to make here is there could be unresolved point sources far below the detection threshold that are contributing to the excess. And the problem is compounded if you, in doing your analysis and extracting the excess, the problem is compounded if you smooth your data, which some of these analyses do. So here I'm smoothing this map with a 2-degree full width half max. And you can see that the excesses are pretty much indistinguishable. You lose all that discrete structure from the point sources. And of course, if you throw the background on top of that, well, these look pretty similar. Okay, right, but going back to our original picture. So, I mean, intuitively we see these are point sources. And why can we say these are point sources? And this is some smooth dark matter background, dark matter profile. And that's because of two things, right? We see that there's a lot of empty pixels with no counts that delineate empty space from pixels that have sources in them. And two, the pixels with sources in them have very high photon counts, okay? So the statistics of the counts are wildly different from a diffuse emission versus a point source emission, right? And by statistics, we can focus on one particular statistic, maybe the easiest statistic of all, and that's simply the one-point function, or the Flux Pdf. That is, I take my gamma ray map of counts, and I just plot up a histogram. And I ask how many pixels contain k photons, right? And so here I'm showing the PDF, this one-point function, for simulated data at high latitudes. And you'll recall at the beginning, at high latitudes, we saw there were a lot of point sources that are easily distinguishable by the eye. These red spots here, these are AGN, etc. And what do these look like in the PDF? Well, these pixels contain high number of photons. So you see that point sources contribute to this high power law tail in this statistic in this PDF. Whereas if you look at only the diffuse emission, there's some variation coming from the galactic component, but this is pretty much Photonian, right? And so if you plot the PDF there, this quickly falls off, right? So the idea is you place your detection threshold somewhere here. You know that the very bright things are definitely point sources, but even below the detection threshold, there's some difference between these two PDFs. So the statistic can distinguish between diffuse emission and point sources, which is exactly the test that we want if we want to distinguish between dark matter and, say, pulsars.
Does your flux, I mean, that just counts the number of photons. Is there a, energy cut applied?
Right. So you could, so here I'm taking the integrated flux. You could also plot this PDF as a function of energy, and depending on the spectrum of these point sources, this thing will change. Right? That's a good point. It turns out that you only have so many number of gamma ray photons to work with, though, so there's a balance. Okay, so actually maybe let's take a second look at this plot, see what's going on here. I told you this is a simulated map of the high latitude sky, and here the blue histogram shows the PDF for the simulated data, and here the green shows the theory curve for the diffuse PDF, and the red shows the best fit theory curve for a model with diffuse emission plus point sources. So how do we get these theory curves? Well, so there's a little bit of math behind it. I promise this is the only slide in my talk, I think, that has this many equations. So what we're trying to find is this PDF, right? This P of k. And this is the probability of finding k photons in a given pixel. If I multiply this by the number of pixels in my region, I get exactly that histogram on the last page. It turns out there's a nice paper by Malyshev et Hogg a few years ago that worked out how to find such a P of k function for various components in the sky. So for example, if you have uniform emission, your P of k is just Poisson, right? If you have diffuse emission that varies over the sky, as is in the case of galactic diffuse or a dark matter intensity profile, then it's just sort of a pixel-weighted Poisson average, right? Here you have an intensity profile that tells you the mean number of expected counts you have at each location in the sky, and in each individual pixel, the PDF is Poisson, the average of all your pixels. Okay, the case for point sources is a little bit more involved, and it turns out to depend on this function here, dnds. So dnds is the number of individual sources that have a given flux S. So it's the flux distribution for individual sources. And you throw this into this formalism, and you can get the PDF for the point sources. Now, it turns out for most cases of interest, you can parameterize this flux distribution with a broken power law. And it turns out that you need, with a broken power law, and so you need 4 parameters to specify your point source model. Okay, so that's the math behind the PDF. So let's go back to this picture. So again, this is the PDF at high latitudes, right, where the point sources are easily visible by eye. And second of all, the diffuse emission and the isotropic emission in this region is low, right? So you might ask, is it possible to apply this test in the galactic plane or indeed at the galactic center where the diffuse emission is much more dominant? And so that's a question that we sought to answer in this paper. Okay, so what does this PDF look like at the galactic center for NFW distributed sources? So here I'm showing, again, simulated data. Here is our dark matter excess. Here is point sources. And here are point sources smeared with the point spread function of the instrument. So this instrument has limited angular resolution. It's a pair conversion gamma ray telescope, and so you can't reconstruct the direction of the incoming gamma rays. So you see that these are quite different. This is smeared out a little bit, but the statistics are still quite different than that. Okay, and now if you plot the PDFs of the simulated data, you get the histograms here. Again. So green histogram is for the NFW diffuse emission, and the red and the orange are for the point sources with and without the PSF, respectively. And additionally, drawn through those histograms of the simulated data are the theory curves for models.
Are those 2 degrees on the side?
Sorry, so here the scale is 10 degrees. This region is from 5 to 10 degrees. So maybe I should say, in doing this analysis, we're looking at statistics of pixels and photons, right? So you need indeed enough pixels before you can do such a test. So you can't really apply this right at galactic center because you have too few pixels. So the idea is to look at the inner galaxy region and see if you can distinguish point sources. Okay, so you can see that two things. Even with the point spread function, the PDF of the point sources is quite different from the PDF of the diffuse NFW. And second of all, that our theory curves are working quite well to reproduce the simulated data. So we can have confidence in Dimitri and David's paper. Okay, now what does this look like when we throw the diffuse background on top of it? So here I'm showing a simulated map of the diffuse counts, and I'm throwing that exact same map on our 3 previous pictures. And again, we can plot the PDFs for these. Here I'm not going to show the histograms for the simulated data, as that would crowd the plot, but I show the theory predictions which do reproduce these simulated curves, simulated histograms. So here you can see the blue PDF is that for the diffuse galactic emission only. Green is for diffuse plus diffuse dark matter. Red is for diffuse plus point sources with the PSF, the point spread function, and orange is without the PSF. Now, we're trying to distinguish between dark matter and point sources, so we're interested in the differences between the red and the green curves. And so you can see that, depending on where you are in the photon count, this can be quite large, of order 10%. For most of the range, it can be quite small, so order of percent. So we're trying to use statistics to track down percent level differences in the PDF. And so one important thing to distinguish what we're doing here from case at high latitudes is, again, at high latitudes, the diffuse emission was much less dominant, and the differences between the parallel tail of the point sources and the diffuse only cases is quite large.
So what particularly the physics of difference?
So the dips here.
Compared to come, right? This GLTV.
Right. So there's an actually. Right. So if you remember when we were looking at the, maybe I'll just go back to it. Right. So again, we said what's different between these two pictures. One, you've got more empty pixels, right? And two, you've got more very bright pixels, right? And so flip back to here. This is the relative difference between the point sources and the diffuse case. And so you can see that this bump here is coming from the fact that you've got more bright pixels. This bump here is coming from the fact that you've got more empty pixels. And the reason why it has to go through 0 is because this thing is normalized, right? So these pixels have to go somewhere. So they get shifted from the middle out to high and low photon counts. Okay, so the game is to take the data and to distinguish between these two curves. And a nice framework to do this in is in the framework of Bayesian model comparison. So this is to say, I can write down a model with one parameter that completely captures our model for the diffuse emission, our model for the PDF of the diffuse emission with the dark matter component. And this one parameter just controls the over-normalization of this NFW profile. Now, as I told you before, the point source models are a bit more involved. We can parameterize these using either 1 or 4 parameters. The 4-parameter model is if we let all the parameters of this broken power law vary, and the 1-parameter model is if we just fix some of these parameters and let, again, the normalization of the point source component float. Now, we throw this into our Bayesian framework, and what we get is a number called the Bayes factor. So this Bayes factor is supposed to give you an idea of which model the data prefers more. And here I'm plotting the Bayes factor in favor of the point source model as a function of the break in this broken power law. Okay? So there are 2 curves plotted here. One is comparing this 1-parameter point source model to the 1-parameter dark matter model. That's the green curve. And the second is comparing the 4-parameter model, point source model, to the 1-parameter dark matter model. So you can see some interesting features. One is when the break in the point source distribution is bright enough, it's very easy to distinguish the point sources. You can easily look at the data and say, yes, this data prefers the point source model over the dark matter model. However, as you go down to lower and lower breaks, lower and lower maximum luminosities, then it becomes harder to distinguish between the two. And in fact, the blue curve shows that the point source model is in fact not preferred in this case when the data is non-informative. And that's simply because, well, you've got more parameters, so you should be penalized. So this is, you can think of this as an Occam's razor, right? If the data can't distinguish between the two models, let's pick the simpler one, which is dark matter. Right, so this was the result of our first paper, which was a theoretical study using simulated data of whether or not this PDF could statistically distinguish between the two cases. And so now, with Tracy and Wei at MIT, we're trying to apply this analysis to the real data. Okay, so what does the PDF of the data look like? So here, you probably can't read the headings, but I'm plotting the PDF of pixels in galactocentric rings. So this first plot is for pixels from 4 to 6 degrees away from galactic center, 6 to 8, 8 to 10, and so on and so forth, all the way out to about 30 degrees. And the blue curves here are the actual data. So again, this is the number of pixels that have a certain number of photons in each ring. And green is the best fit dark matter model. So the PDF for the best fit dark matter model in each of these rings. And again, what we're looking for is, in the inner galaxy, 10 or 15 degrees, are there excesses at the high K end of the PDF? So if you squint at this a little bit, I'll let you draw your own conclusions.
Which would be indicative of point sources in addition.
That's right. Okay, maybe I'll say, here at far away from galactic center, it seems the green and the blue curves match up decently well. Here, when you're getting closer to 10 degrees within the galactic center, it looks like there's some strange excesses in the data. But again, this is all very preliminary.
This is dark matter only, right?
Right, right.
So there's intersimulated analysis should do anything. So.
Right, so you can ask, well, maybe you can have models that have some dark matter and some point sources, and you can maybe try to pull out the respective fractions of the two. I think the answer to that is the data probably is not going to be good enough to do that. Like you might pull out, so I didn't say it in the beginning, but the excess is only about, depending on how you run the numbers, 10% of the total flux in the inner galaxy, right? So you might pull out, oh, dark matter is 5% plus or minus 2%, and point sources are 5% plus or minus 2%. So the data is not good enough.
Do you feel that some sort of significance factor on the difference between the model and data?
Right. So now what we're doing is we're using that Bayesian framework.
Right.
Here I've only showed the dark matter model, and we're trying to run this analysis and say how much does the data prefer the point source model if it does it all.
Right.
Right. And so this is something I'm showing in the next slide. So here what I'm doing here is a little different. So before we were just concerned with looking at the galactic center, but in order to make sure we understand our test a little better, we're going to make it a little more general and say, let's look at patches over the sky and just see whether extra point sources are preferred or extra just diffuse emission is preferred. Okay, so here at the top, this is a map showing the excess over the background model, right? And so you can see that there's an excess at galactic center of order of 10%. Probably can't read this here, but this is 10%, it's red. But the model is not a great fit for over the entire sky. And so there are actually excesses everywhere, right? And so you might ask, well, given that we have this test to distinguish between excess point sources and excess emission, is there any reason why it fails at the galactic center only, or does it fail on the sky, or are the results consistent over the sky? Right? So that's an important test to do. I mean, you could also step back and say, well, we have all these excesses. If we try to fit an NFW profile around one of these excesses, do we get dark matter as well? I don't know if anybody has tried to do that. Maybe not. But okay, so what we did is, so we have this test looking for extra point sources over the background model of the sky. And this is the plot corresponding to that scan. Here I'm showing the fraction of excess flux that gets absorbed into the point source component of the model. And so you can see while there are some fraction of flux is going to point sources at galactic center, indeed there are other regions in the sky where it seems like there could be extra point sources not accounted for in the background model or in the catalog. And here on the right, I'm showing this Bayes factor. So comparing the preference of the data for the point source model, the model with extra point sources, over the model with just extra diffuse emission. And so there's a quite prominent region there too. But again, I stress this is really preliminary, and we're trying to make improvements to both the calculation and the way we apply it to the data. For example, you mentioned energy dependence. We're also looking at that. And so this is constantly changing. It's plots are only made.
Curiosity is the one parameter.
So this is the 4 to 1, right?
Okay.
Right. So the fact, so this is a log scale. So
Right.
this is e to the 3 here at the log center.
To 10.
Sorry.
Sorry, to go to the log, it's 1.
Right. So this is at the Galactic center. This space factor is about 20 to 30.
And over 2 is when things would get interesting.
Right. I mean, so yeah. So the space factor is sort of an empirically scale model. So here I had some I don't know, criteria on the side. If your base factor goes, is exactly 1, neither model is preferred.
Right.
If it goes above a few, well, then you've got weak or substantial evidence, strong evidence if you're above 10. So, but again, this is empirically calibrated, and it doesn't have like a clean interpretation like some frequentist statistics do. Okay. So that's the point source stuff, and again, it's ongoing. And I think Tracy will be coming in a month or a little over a month, so she may confirm that there are indeed point sources at the Lincoln Center, or she may confirm that we had some bugs in our code. So it remains to be seen. Okay, so now I'm going to talk a little bit about wavelet decomposition. And so this is a project with Sam, Elias, and Patty. And again, this is to test. Primarily, the idea here is to test this hadronic astrophysical scenario, this hadronic cosmic ray injection at the Galactic Center. So again, I told you that that an injection of cosmic ray protons, which interact with the dust and gas, diffuse this extra emission associated with the dust and the gas, and that this is already kind of not preferred by the best fits the model, which prefer smooth NFW excess. However, we can start to ask, can we apply tests to better characterize the excess and say whether it's more dusty or more smooth, right? So before we were asking if it was more point sourcey or more smooth. Now we're looking to see if it's dusty and has structure on small scales. Okay. And so it turns out you can use wavelets to accomplish this. But before I tell you about wavelets, let me step back and tell you about the template fits that were used in many of these studies. So how is this excess extracted? You start with spatial templates of your background, which includes the diffuse emission and the bubbles, and then you have your NFW template. And now you focus on a certain energy bin, and then you do a fit for all of these components, and then you extract spectra, right? So you say in this energy bin, I've got 80% this, 10% that, 5% that. In another energy bin, it makes it different. And so you can reconstruct the spectra for all these components. And the thing that makes you suspicious about the extracted extracted by this component is that it has this lump, right, this feature that looks like dark matter. Right? So that's the template analysis. Alternatively, you could fix the spectra and then scan over rings in space, right? So before we were fixing the spatial information and trying to extract the energy information. Now we're doing the opposite, fixing the energy, trying to extract the spatial information. So this is the ring analysis that was done in this paper, Dylan et al. So what they showed is if you assume there's a component in the sky that has a bumped feature, and you reconstruct it over the sky, you get something that looks like an NFW profile. Okay, so that's sort of indication that these two methods of extracting the excess are self-consistent, although they do get slightly varying results, for example, for the power indices of these NFW profile, etc. Okay, so I guess the point I want to make here is this template technique takes into account spatial information and energy information. But if we're interested in trying to characterize the angular properties, or the angular scale properties of the excess, we might want another dimension of information, angular scale. And so that's what wavelets provide. Okay, so I'm going to show you a series of slides I stole from Sam McDermott, give you a quick introduction to wavelets if you don't already know what they are. So you can think of wavelets as basically a beefed up Fourier basis, right? So you've got some functions that have some nice properties. And these functions are, the coefficients of the functions in this basis are a function of not only scale, as in the case of Fourier analysis, but also a function of position. So while the Fourier coefficient tells you, oh, I've only got power at a certain frequency or a certain scale, this also tells you, Wavelength coefficients also tell you where that power is in space. So we can see an example of that here. So here I'm showing a simple sine wave with one fixed frequency. Take the Fourier transform of this thing. Here I'm plotting the coefficient, Fourier coefficient, as a function of frequency or scale. And you can see, yeah, this thing has one frequency. It's got power at this specific scale. If you take the wavelet coefficient of this thing, the wavelet decomposition of this thing and plot the wavelet coefficients, these things are not only a function of scale, as this thing was, but also a function of position. So this position here corresponds to this position here. And you can see we've again got scale at this power. We've again got power at this scale, and this power occurs everywhere in space, right? Now what happens if we've got a superposition of sine waves? Well, in the Fourier case, now we've got two spikes in the Fourier coefficients, right? We've got power on both of these, at both of these frequencies. And in the wavelet decomposition, again, we've got two spikes in scale or frequency. And again, these things occur everywhere. We've got power everywhere at both of these scales. Now, the things that, the information that wavelets buy you is, for example, what if you've got a case like this, where you've got power in one frequency only at a particular location, and power in the other frequency at a different location. If you take the Fourier transform of this thing, well, you get spikes here. You might get a little information from the width of this spike about how this thing varies, how you have some variation here. But you really lose the spatial information that, yeah, I've got a signal here with a given frequency and a signal there with a completely different frequency. But when you take the wavelet decomposition of this thing, you still retain that spatial information. So again, we see peaks corresponding to power in these two scales, but they occur at completely different positions corresponding to the actual positions. So this is the nice property of wavelets, right? And so, right. So the idea is now to apply this to the gamma ray data, the gamma ray sky, which is a function of position and also energy, right? And so, as opposed to our simple 1D case, we've got additional dimensions of information here. So we've got the 2D spatial information on the sky, and also a third dimension of energy. And we want to break down the spatial information using the corresponding wavelets on the sphere. Right? And it turns out that you can do this. There's a nice formalism set up, and this is what the wavelet coefficients of the gamma ray sky look like. So here, I'm plotting the wavelet coefficients as a function of position on the sky at different wavelet scales. As I go up here, you can see where on the sky is there power at a particular scale. I'm doing that in different energy bins, right? And so this really tells you, yeah, in this location I've got a lot of small scale power, maybe not so much here, where away from the dust, for example.
What like the Bayesian energies?
So here I think, also actually I think this was simulated data. This is just a schematic example. Here I think we just plotted the Galactic model in very large energy bins. Right. So again, I think our modus operandi here is going to be to try to understand this technique on simulated data before we apply it to the real data.
That's Galactic.
So this is Galactic. Yeah. Okay. So now let's focus on the inner galaxy region and see what wavelet decomposition there might look like. So how does this look like if you've got an NFW excess and you take the wavelet decomposition of it? So here, there's like a 10 by 10 degree region again, 10 degree radius region. We take the wavelet decomposition of this and we plot sort of a chi-squared. We make a chi-squared plot. Okay, so here, again, I'm showing different energy bins along this axis. And again, different wavelet scales on this axis. And what we do is we take a background map, throw a smooth NFW axis on it, simulate some noise on top of that, and then take the chi-square to that with respect to the background. Right? And so you can see at this finest wavelet scale, we get a lot of excess chi-squared, and that's simply coming from the noise. So wavelets are a great way to denoise your data if you've got Photon noise topology. Now, the other thing you can see is that this NFW excess that we've injected has a particular spectrum. We injected one with a bump, and you can see that this shows up here, right? So in all of the energy bins, you get an excess corresponding to 2 to 10 GeV. And finally, this excess, because this is a smooth thing that you're injecting, occurs at these larger scales, wavelength scales, right? So this sort of plot is a nice way to characterize the angular properties of the excess without having to resort to any particular background model. You just make this plot, subtract the, your best idea of the background model, and you see, well, this thing has power on these scales and these energies. So how does this look like if we've got a hadronic burst and the dust is getting lit up? Well, now the dust has all these filaments and all this small scale structure, and if we assume that it still falls off as an FW, it still has the same bump, but it just has now this additional small scale structure, this chi-square plot now looks very different. So you can see the bump in energy is still coming in the same energy bins, but now we have much more power at small scales. Right? So this would be, this is a powerful way to characterize the angular properties of the excess. Another thing that we've been playing around with is whether or not you can use these wavelets to find structures. So now let's move away from the center and just look at the entire sky. Again, I told you we've been playing a lot with simulated data, trying to understand how to best use these techniques. And so what we've been doing is what we call the Weyland Olympics. So Ilias, he hides his cards, he simulates some background, throws some random signals in there, and then we try to apply the Wavelength techniques to extract the structures he's put in and determine their spectra and see if this technique is robust. So here's one example of an Olympic trial. So here I'm showing, so this again is borrowed from Sam. Here, these are both showing the simulated data with different contrasts. Here's the mock data at the highest wavelet scale only. And then here's what the average diffuse template subtracted. So you can see at this highest wavelet scale, you're mostly pulling out Photon noise. Right? Now if you start sweeping to larger and larger scales, you can see some interesting features. So here you can see that Ilias stuck in a Fermi bubble template in this particular simulation. And actually, if you look really closely, you can see this nice edge along with the interior bubble structure. So I think it's still an open question whether or not the Fermi bubble has indeed this really nice hard edge. And so Ilias was trying to put this into the data to see if we could tell between the two scenarios, edge, no edge. But he had a minus sign in his code, right? So you can see that the edges don't line up. So the punchline here is that even with Photon realization noise, you can pick out differences like minus signs in the universe with these wavelength techniques. So they're quite nice. Okay, so to summarize, we've got this GeV excess. It's very mysterious. Seems to be robust. Doesn't seem to be going anywhere. It could be coming from dark matter annihilation, or it could be astrophysical. And I think, I really would like it to be dark matter annihilation. I think many of us feel the same way. But in order to be really confident that it's a robust detection, we got to rule out as many other alternate scenarios as we can. And so I showed using photon statistics, we can rule out or constrain point source contributions to this excess, such as those coming from millisecond pulsars, or those coming from some completely new class of gamma ray point sources at the Galactic Center. And with wavelet decomposition techniques, we can better understand the angular characteristics of this excess, and perhaps try to rule out scenarios involving hadronic bursts, etc. Thank you.
Thanks. That was really tough. So is there any more questions?
So maybe you could go back a few slides for me. I actually have way too many questions, so if you guys want me to shut up. Can you go back to slide 29? You mentioned something about smoothing on this slide.
Right.
You called it something, but it went by too quickly. Was it like some kind of paranormal density?
Right. So I think the idea here is the data. So even this schematic picture I showed you here has been smoothed by the PSF of the instrument.
Oh, the instrument. Okay.
Right.
And is that just like a smearing, a noise added?
Right. It's
Okay.
a smearing.
All right.
the simulated data I showed here is more of like what the data looks like without the raw data.
Okay, so when you said you used data smoothing, it was just sort of to simulate the detector? Is that what you mean by?
So to simulate the effects of the detector, there is some smoothing applied even from going from this to this.
Right.
Right.
Yeah.
The point I was trying to make in this slide is that when people do these template fits, they apply smoothing to the data to make it a little more nice and make the template fit a little more nice.
Okay.
I have to qualify, only certain analyses do that. But the point is, if you choose your smoothing to be too large, of course you're going to completely wash out.
Right,
the
right.
sources.
Yeah, so it's, I don't know, it's just funny that, it's a shame that you won't be here tomorrow, because my talk tomorrow is about smoothing.
Oh, is that right?
So, but I haven't done 2 dimensions yet, so it's really
Yeah.
interesting.
We have the
Yeah, so, but anyways, I'd like to talk about
Okay, yeah,
it.
great.
So maybe if there's anyone else who has questions.
Yeah, sure.
For now, then we can come back to it.
I was just curious if you're in the residual point source analysis, if you actually went and looked at anything in that part of the sky that could
So,
be
for this one.
the other 3.
These other regions, right? So, I mean, the thing is, this is just a statistical test, right? So what we do here is we mask out all the no point sources, right? The ones that are clearly above the detection threshold. And so, if you look back at the PDF plots, there's some stuff out at a very high K that is obviously a point source, right? And so we're really only using the stuff that is, could be a point source, it could just be a very bright region of diffuse emission. So it's really hard to say, to look at a region and say, yeah, these pixels definitely looks like this region has more bright pixels with point sources. And perhaps that's an important point to make. So I framed this in the context of looking for point sources, right? But really, the only thing that this test can tell you is that there's structure in your diffuse or in your data that's below the pixel scale, and that's not accounted for in your model, right? So that's a very important distinction. These could be true point sources like pulsars, or they could just be really tiny molecular clouds that are lighting up. And with this sort of test, you can't distinguish between the two.
Some of those. So you wrote papers on some of those, but if you include these in your maps.
Right. So indeed, the reason the way I got involved in this PDF business is before Fermi even launched, I wrote some papers saying, you can use the PDF to look for dark matter subhalos. These things will also look like point sources that have some different statistics. Before Fermi launched, we were pretty confident, I think, that we were going to see tons of subhalos. It turns out not to be the case, but I still wanted to apply the knowledge I accrued.
But including those, like let's say you include those on top of your
Right.
prediction for those, that doesn't change these.
So yeah, I mean, you could argue, well, maybe this is coming not from small molecular clouds, but from dark matter substructure. But yeah, I mean, that would be an interesting thing to learn, right?
I have a question. Go back to your, I think the first slide where you show the excess.
So the very first slides.
Yeah.
Yeah. So these are from Dialon et al.
No, just the 2 GeV excess.
The structure.
So here, people assume some background model and then do the subtraction to get this. Now, first, there are a few things that I think it's not very robust. First of all, the uncertainty is only statistical, then we don't use systematic uncertainty. Second of all, when you take a profile like a FW profile, which is exponential rising, right, then you convolute that. You have to convolute with the acceptance because that's what you see, that's what you detect, right?
Right.
So you take an exponential that's going up, and you take an acceptance that's sharply falling down. When you convolute, you are guaranteed to come up with an excess somewhere.
Right.
Or the crossover.
So you might argue, well,
And we see that even in dark matter detection. Exact same thing.
Fermi's energy range is, I feel like 30 MeV to hundreds of GeV, right?
Yeah. But that's at the low end. You see,
Right.
GeV is sort of accepted. I don't know if you have an acceptance curve, because when you do this 2 convolution, is a sharp acceptance fall with exponential. We have seen that feature in many things.
Right. I mean, you might, given that you have data that's sharply falling off, right? Where would you find an excess? Well, it's not going to be at the low end where you have lots of data to understand.
It is at the low end.
Right. Well, I mean, the fact is that it's coming. You're not getting very many of that.
Right. Exactly.
Right.
That's the
Right.
That's why it's kind of suspicious, but again,
Oh yeah, lots of things are suspicious.
I mean, I guess that's an independent question from like the systematics of the model itself. Like
Yeah.
the model is based upon the correlating emission of like molecular clouds, gas maps from other wavelengths. You don't really have spatial resolution that you need to make accurate predictions for
there
outcome here.
are the astrophysical uncertainties, but also when you just take purely
Yeah.
the distributions itself,
Right.
on
That's
with
yes,
acceptance,
exactly.
you're guaranteed to find an excess at some point.
Right, so this, I think this is an interesting statistical question. Right? Yeah, here I'm showing this plotter that the Galprop systematics are taken into account in these blue curves. And so these authors make the argument that even when you account for the systematics, the axis is robust.
Maybe we'll take one more question.
Okay, so the one other question that would be of interest to everybody here is this Bayesian test you were mentioning.
Yeah.
You said that it's maybe not quite as unbiased as a frequency test.
Well, I said that there's not as clean of an interpretation, right? So,
Right. So, but usually the reason that there's not as clean an interpretation has to do with the prior. So is there some prior in here that you
Right. So we assume pretty reasonable prior. So all of the parameterization is going into this broken parallel.
Okay.
And so you've got normalization, the location of the break, and the two parallel indices, right? And
Okay, so about 4 parameters.
right, and the parallel indices can only there's a certain range that's physical, because if you allow these to go too far, then you've got infinite flux or something like
Right.
that. Right. So there's a natural range for those guys. The natural range for the location of the break is, well, you can't be too low, you can't be below 1 photon, because then you don't really see anything, right? And you can let this extend up to hundreds of photons, however high your
So are they like for those parameters that have a range, or you just like
right? So these are
keeping the range but flat prior?
flat priors for those, and long flat for normalization.
Flat for those ones. Yeah. Okay, that makes sense.
Yeah. I mean, I think that, yeah, so all of these things are a little arbitrary, but I think
Yeah,
those
of
are
course.
reasonable.
Yeah.
But yeah, so again, there's not as clean as I mean, if you get a base factor of 20, what does that mean? Well,
Right.
yeah, so I think in the end, it's just this, statistical nudge.
You need to change your priors to see if you get.
Well, yeah, so.
Have you thought about using like a likelihood ratio test for this?
Right, so
To be a little more robust.
right here we've got 4 prayers and 1 parameter, so.
Oh, I see.
So that's the other reason why this is nice, too.
Yeah,
The
yeah,
likelihoods
okay.
don't have to be nested.
I get it.
And then this is nice because it allows me to test different models.
Right.
That's
Yeah,
what it uses
yeah.
Bayesian.
Yeah, that's right.
And it's sort of this is the integral of the
Of the evidence.
it's the likelihood of the evidence.
Right.
So it's something akin to what are the absolute values of chi-squared for 2 sets of models.
Right.
It's an empirical way to compare those two. That's
Yeah.
why I pulled it.
Yeah. Okay, I get it.
But this doesn't have a clean curve.
No, it
If you
doesn't.
say chi-squared is x, then you know that has some statistical.
Right.
Base
If you believe your model.
Right.
And if you believe that your chi-squared statistic follows the chi-squared distribution.
That's
Right.
it.
Okay, so before you generate too much into argument, we'll hold the discussion here and take any questions offline. So thanks, Sam, again for the talk.